In a previous video, I introduced the concepts of function. In this one, we're just going to continue on and talk about some other things about functions. So first of all, here we're talking about increasing, decreasing, and constant, and what that means when you're working with a function, as well as relative minima or maxima. Those are plural words. We usually have a maximum or a minimum. That would be singular. So here it says we say a function is increasing on an interval. This is an interval of x values if it rises from left to right. So this is very intuitive. This makes sense. And that's how we read. We go from left to right. So let me draw some grids here. So this would be an example of a function that's rising from left to right. It's currently increasing on this interval. Another way to say this is as x increases, y increases. So as x is getting bigger, so is y. We say a function's decreasing on an interval of x values if it falls from left to right. So that one would look like this. And again, an alternative way to say this would be as x increases, y decreases. And then finally we have what we call a function being constant, and that's if its value is constant or the outputs are constant. So here notice all the y values of this function are the same on this interval. So as x increases, the value of y remains the same or constant. Alright, so let me show you. If you look at this formal definition here, this is like what you'd see in a calculus book. It says a function is increasing on an open interval I if for any values x sub 1 and x sub 2 in the interval, x sub 1 less than x sub 2 implies that f of x sub 1 is less than f of x sub 2. So let's look at the picture to help you understand this here. So first of all, we're looking at some interval. This is our I here, our interval I. Notice x sub 1 and x sub 2 are in this interval. And you can also see that x sub 1 is less than x sub 2 because it's to the left of x sub 2. Now let's look at the points up above. So here, this is the point that has x sub 1 as its x value, and the output would be f of x sub 1. And then for x sub 2, you've got the point x sub 2, f of x sub 2, which is just the y value when our x value is x sub 2. And if you look at our outputs, f of x sub 1 and f of x sub 2, basically we're just looking at the height of the graph here. So you can see that f of x sub 1, the y value there is smaller than the y value for f of x sub 2. So what we have here is that f of x sub 1 is less than f of x sub 2. So in this interval, if you pick any two values where x sub 1 is less than x sub 2, then it's always going to be the case that f of x sub 1 is less than f of x sub 2. And so this is a way that we can formally indicate when a interval or when a function's increasing on an interval. So you'd have a similar type of definition for decreasing and constant. Alright, let's move on. So here we're talking about relative minimum. Well, we don't say minimums or maximums, we say minima and maxima. These occur at peaks or valleys, or what probably a little more formal would be the word turning points on the graph of a function. So for example, here you can see that we have a maximum that's going to occur at this highest point. You're going to have the highest value for y. In fact, notice it says, so we are going to have a relative maximum. Notice here it says a relative maximum or minimum is the y value at such location. So at these turning points, in this case, you can see the y value is 1, we also like to explain where it's at. It occurs when x is 0. So we would say there's a relative maximum of 1 when x equals 0. So that's how we would describe that. Now let's look at g, and you can see here we have a relative minimum. So this is what I'd call a valley, but again, or a turning point. But this time we're going to have a minimum. So relative minimum here, and again the y value is -3, and this one occurs when x is 2. So notice when x is 2, we're down 3. That's where we have our relative minimum. All right, and so you might try doing the last one there. Let me go ahead and do it now. So we have a relative maximum here. So it'll be a relative maximum of 1, and that's when x is 0. We also have a relative minimum right here. So we're down 3, so we have a relative minimum of -3, and that's occurring when x is at 2. Now, what we're talking about here are relative minimums. Like for example, on the problem we just did, in this area, this is a relative maximum. Notice this graph continues up forever, so it's not what we'd call an absolute maximum. There are points on this graph that have a higher y value. But in this region, this region right here that we're looking in, this is a maximum for that region at that turning point. All right, and then the same thing would be true down below here. In this region, we have what's called a relative minimum. Since this graph continues down, it's not what I'd call, or what we'd call an absolute minimum. But in the region we're working in, or in this region where we have this turning point, that would be considered a relative minimum. Notice the first problem we did, we actually have not only a relative minimum, but that's actually considered an absolute maximum. It is the highest y value for the whole function. Same thing's true on g. This is an absolute minimum as well as a relative minimum. So our focus here though is going to be on relative minimums, and they just occur wherever you find these turning points. Alright, so let me erase these marks and let's talk about increasing and decreasing. Let's look at the first function here. I like to work from left to right as I do this. So notice on the left of this function, let me put these arrows in. Remember, this graph continues down to the left on the left side and to the right on the right side. So going from left to right, you can see we're increasing, or this function's increasing. And that's occurring when the x values go from -infinity until x is equal to 0. And so we say we're increasing on the interval from -infinity to 0. Now, after x reaches 0 at this turning point, now you'll notice, well, actually, let me make a note here. I want to remind you that when we talk about where a function's increasing, decreasing, or constant, we're talking about intervals of x values. So let's look at where we're decreasing here. So when x is 0, we're at that turning point, and then from now on, as x gets positive and bigger, this function is decreasing. So it's from 0 to infinity that this is taking place. So we say that the function's decreasing on the interval from 0 to infinity. All right, let's look at g next. So let me darken this in a little bit and put some arrows in. So going from left to right, you can see from -infinity until, well, let's see, until x is 2, this function is decreasing. So from -infinity to 2, the function is decreasing. So now at 2, we have a turning point, and now we're increasing. Notice this function's just increasing when x goes from 2 to 4. So we'll write increasing on the interval from 2 to 4. And now notice once we get to 4, an x value of 4, this is a constant function, or the function's constant, and it's going to be that way from now on. So from 4 to infinity, the function's constant. So we say it's constant on the interval from 4 to infinity. So again, I would encourage you to maybe try the next one and then turn the video back on. Alright, so let's do this. Let me put some arrows in here. So going from left to right, you can see we start by increasing. Now this thing almost looks like it's going straight down, but it is going to the left. So from negative infinity until x gets to 0, this function's increasing. So increasing on negative infinity to 0. And then notice now we're going to be decreasing from when x equals 0 to 2. And then notice now we're increasing again. And again, this is going to the right forever, even though it's rising a lot faster than it's going to the right. So we would say from 2 to infinity, so when x goes from 2 to, from there on, the function will be increasing. So from 2 to infinity. Alright, let's move on to the next page, or next slide. So here we're going to talk about symmetry and the definition of even and odd. So it says here the function f is an even function if f of minus x is equal to f of x for all x in the domain of f. Well, let's break this down. So first of all, let's look at an example. F of x equals x squared. This is an example of an even function. So let me show you how this works. So first of all, I'm going to go ahead and graph this function. We'll be working with this function a lot very soon. So what we're saying here is if I plugged in a number like 2, that'd be 2 squared, and I would get an output of 4. And if I plug in the opposite of that number, so if I plug in negative 2, notice we're going to also get an output of 4. So this will be true for any number and its opposite with this function. We're going to get the same output whether we're plugging in the positive or the negative. So a picture of this, this would be some random point x comma f of x. So on the other side, at minus x, notice we're up the same height. This height here is the same as this height here. In other words, our y values are the same. Of course, we call our y f of x. That's our output. So we're getting the same output whether we plug in x or its opposite. So anytime you have a function like that, you have what's called an even function. And notice if I put a dotted line down the middle here, whoops, that's not a very good dotted line. Let me see if I can do a little bit better. So there's a line of symmetry there. The right side is basically the mirror image of the left side. And this is what you're going to have with even functions. So we say that the graph of an even function is symmetric with respect to the y-axis. Alright, let's go ahead and look at the other definition here. It says the function f is an odd function if f of minus x equals minus f of x for all x in the domain of f. So again, we're basically plugging in minus x into the function, but notice this time we're not getting f of x, we're actually getting the opposite of f of x. So let's look at an example to make sure we understand what's going on here. So here we're going to look at the function f of x equals x cubed. This is an odd function, and let's talk about why. So if I graph this function, again, this is another function that we're going to get to know quite well. It's got kind of an S shape, or kind of a snake-like shape. But let's look at what happens here. If I plug in 2, I get 2 cubed, which is 8. So what happens if I plug in the opposite of 2, which would be negative 2? So it'll be negative 2 cubed, and if you multiply 3 negative 2's, you actually get negative 8. So we don't get the same number like we did in the example up above. we actually get the opposite output. And so in general, if I have this point x comma f of x, if I plug in minus x, what's my output? Well, it isn't f of x, it's actually minus f of x. This distance here is the same as this distance here, it's just here we're going down, it's a negative y value there. And so that's going to be true for any point that you have in the first quadrant. You're going to have a point in the third quadrant that you've got some kind of symmetry going on here. We'll talk about that in a second. So let me go ahead and write this. The graph of an odd function is symmetric with respect to the origin. So let me show you how that works. Of course, the origin is the point 0, 0. Let me write that right here. And you could actually draw a line. See this line here? It goes through the origin, and basically this distance here, it's going to be the same distance on the opposite side to a point. So we have symmetry through a single point. In fact, another way to look at it is you could actually put like a tack here, or if you could, and you could rotate this thing around 180 degrees or halfway around. You would actually be back to where you started. So it can be considered rotational symmetry, but we tend to say that's symmetry with respect to the origin, or just that one point. So for any point on this side, we can find a point on the opposite side through that point, through the origin. Alright, so let's go ahead and move on. In here it says, determine whether each of the following functions is even, odd, or neither. Then determine if the graph is symmetric with respect to the x-axis, the origin, or neither. So when we do these kinds of problems, we're going to use what's called the algebra test. So first of all, we want to replace x with minus x and simplify. So then we have three possibilities. We're either going to get f of x as our output. That's like the first example I did up above. That's for even functions. Or we'll get the opposite of f of x, and that was like our second case where we had an odd function. Or we could possibly get neither of those, and in that case we'll say neither. So on number one here, let's go ahead and make a shell. So wherever there was an x, now there's parentheses, and let's replace x with minus x. Well, minus x cubed, we're going to multiply 3 of these minus x's. Well, a minus x times a minus x will give you a positive x squared. Positive times a negative here, we're going to end up with a negative x cubed, or a minus x cubed. This is always going to be the case when you have an odd number of negatives. So it's going to change the sign of our term. This will become minus 2x cubed. And of course, a minus minus x becomes a plus x. So notice if you look at our terms, they're the opposite of what they were. In fact, what we originally had here. So we could actually factor out a negative 1, or just a negative. This is the opposite of 2x cubed minus x, which we could write as minus f of x. So this is the second case. This is going to be an odd function, and that means we have origin symmetry for this function. So without even looking at the graph, we know it's odd, and we know it's got origin symmetry. Let's do the same thing with number 2. So I've made my shell. Let's plug in a minus x. Now, a minus x to the 4th, if we multiply 4 of these guys, notice a negative times a negative is a positive. A negative times a negative is a positive. So when we multiply here, we have a positive times a positive, and we're going to get x to the 4th, positive x to the 4th. And so if you think about it, for any even number of negatives multiplied, because you can pair up each of the negatives, and there's not going to be any left over, you're going to end up with a positive. So for any time you have an even power in a situation like this, you're going to get a positive answer. So a minus x times a minus x, that's also going to be x squared. It'll be positive. My sign doesn't change again. And then finally bring down the minus 2. So notice what we started with and what we finished with is the same. This is equal to f of x, the original function. And so this is our first case, and we're even here. And that means that we have y-axis symmetry. Finally, on the last one here, let's go ahead and make a skeleton. Let's plug in our minus x. So notice the first term changes signs, but the second does not. So in a case like this, see, the bottom line is with even functions, what you get is the same as what you started with. With odd functions, each of your terms change signs. In a case like this, where some of the terms change signs and some of them don't, you're going to have neither case. All right, I'm going to go ahead and stop the video here, and I'll do another second part.